Hello and welcome to the Advanced Conduction lecture series. So today, before starting our actual lecture, I would like to talk about something that I think all of us are aware about, and that is the Archikar rape and murder case. Our sister, who who was a lady doctor in that college, and who was a PGD student, a PG second year student, she was doing her duty, 36-hour long duty, and after that she got the gift of being raped and murdered. Her eyes was not full of tears but full of blood. Her legs were splitted apart 90-degree. So we are studying all these things, right? And we have to be great engineers, great doctors, and we have to be established in our life. All these things are fine, but if we are not aware that we are the one, we are someone who can do the things which are right for the society. We all know that, the political leaders of any state and in the whole India, how they are, what they can do. They will only do what they think that will satisfy their purpose of gaining money and fame, more and more, gaining money and power. So my request is that please don't study these things anymore. Please don't do the work from which you can get money. If you are not aware that you have to fight for her, you have to fight for your own future self, you have to fight for your next generation. If you are still someone who is thinking कि जो हुआ है होने दो, I can do, I cannot do anything, please change your mentality. Actually, I cannot say anything. If you are not changing your mentality, I cannot say anything. But don't think like it that okay, I am in IIT Kharagpur, or I am in there and here. I cannot take part in the marches and protests. That is fine. You don't have to take part. You don't have to do anything that will hamper your career. At least you are in Facebook. You are scrolling. You are scrolling numerous reels and all the things. You are seeing some news about this thing. So share those. Share about the marches. Share about all the things that you think which need to be shared to spread the protest. So I just request you that please try to understand the seriousness of the situation. If you are okay, if you are someone who just thinks about himself or herself, then also I am talking all these things because of you only, for your future self, for your family. Okay, so if you want to secure a good future of yourself, what will you do with a lot of money if you don't have a security? What if you, if you don't have a security, if your loved ones are not having that security? Today it was that sister, tomorrow it can be you or your family member. So please, we have to stand up for justice for that girl, for our didi, for our sister, for our bahan. So I urge you, please stand up. Those of you who will be seeing this video after a long interval from this happening, maybe you are watching this in 2025, for them also you have to ensure that is the society is if the society is going in a right path or not. This kind of instances never become old, never become out of the time. Okay, we cannot forget Nirbhaya, we cannot forget Asifa and all the women who were tortured. Okay, so we have to fight. Hashtag justice for Archikar. Okay, So now let us start our lecture. In the previous lecture, I made some mistake, and I really apologize for that if that has created some confusion for you. But to compensate that thing, I will solve a fresh problem, a new problem in this lecture. Okay, so now let me just take up the question. Clear? Okay, so this was here, this was our problem. I have already discussed it, right? I mean, and I gave this as your homework, but because of my mistake only, I will solve it once more and from scratch. So there is only one difference in the problem if we compare it with the problem that I have solved before. And what is the difference? The difference is the boundary condition here. So let us read the problem once again and we will solve it. Firstly, a semi-infinite solid. So it is infinite in this direction, here it is the positive x, having thermal diffusivity alpha. So a very good practice or habit is to write the information given in the question when you are reading the question. You can write it as a rough work in your question paper or as a formal work. So if you are writing an exam, you can just write that given. This is what I used to do. Given thermal diffusivity, okay, equal to alpha. Then you write thermal conductivity equal to K, and ambient temperature T infinity is suddenly subjected to a uniform and constant heat flux of Q naught. So Q naught is neither a function of space, and nor time. That is why it is written uniform and constant. Okay, and at time t the heat penetrates at a distance delta t. So this is the heat penetration depth, and the instantaneous temperature profile is shown in the figure. Okay, so I think the formulation of the problem is totally understandable. So the part A, we have to write a very obvious things, uh, without which we will not be able to solve the problem at all. So write down the transient governing equation in dimensionless form with appropriate boundary condition. So I have shown for many times that how to convert a dimensional form to into its dimensionless form. Okay, so now I will not do that. And for B, we have to show this, that the temperature uh, profile can be expressed as this. So see the word can be. It is not telling that it should be or it is. I mean, there is no certainty because this is an approximate approach, and that is why it is saying that the temperature profile can be expressed as Tx minus T infinity equal to C1, which is a function of time, into 1 minus x by delta t whole square. We will see that key. I mean, we have to again do some, we have to again propose a temperature profile, and we have to find the constants. And finally, we have to set up the integral equation of the heat transfer suitable for this problem and solve for the heat penetration depth and find the temperature profile. Because in this temperature profile, we will see that this delta T will be the only unknown thing, so we have to solve for that. Okay, so let us start solving the problem. I will solve it a bit quickly because I have already described all the things, most of the things which are required. The only difference is the boundary condition. Okay. Okay. So by the way, if any one of you wants the notes of this lecture series, this is up till now it is of 144 pages, it will go up to I think 160 pages. So you can just mail me at biswas8512@gmail.com. Okay, so you can take a screenshot of this and you can mail me here. Okay, asking. So you have to tell that from which institute you are, and you are studying which course and in which year you are, and you want to see the notes. Then I will send you the notes. Okay. So let us start solving the problem now. Firstly, I will draw a schematic, and this is lecture number 21. Okay, it's lecture 21. So the schematic should look something like this according to the given problem. The schematic is already given in the problem, right? So the schematic will be, let me change this color into maybe yellow. Okay, so this is our semi-infinite block, so I should draw it like this. Okay, and so now this is the positive x. Okay, so it is given that we are giving it a constant heat flux q naught, that is a constant both with respect to time and space. Okay, so firstly let us write the governing equations, which are very obvious. Pause the video and try to do this part by yourself, and that will be del 2t del x whole square multiplied by alpha is equal to del capital T del small t. Okay, now let us write the boundary conditions. Okay, the boundary conditions. So T, do we know T at x equal to 0 for any time t greater than 0? Do we know this? No, we don't know this. But what do we know then? We know that delta t delta x, or I should write minus k delta t delta x at x equal to 0 for any time t greater than 0 is equal to q naught. This is given. And what is the significance of this? This is the, you have started your observation at time t equal to 0, and you are considering any time instant after your observation has started. Okay, and I mean now can you tell me that should this minus be there or not? I am asking you this question. I can also make mistakes. So should this minus be there or not? Pause the video, think about it, and give me the answer in the comment box. So yes, it should be minus k delta t del x, because the heat flux is towards positive x direction, and heat flux towards positive x direction is written by minus k del t del x. Okay, so this is the boundary condition number 1. Okay, number 2, see, at x equal to delta t we can have two boundary conditions. So option A is we can have delta t delta x at x equal to delta t for any time t greater than 0 is equal to 0, or option B, t at x equal to delta t at any time t greater than 0 is equal to t ambient here. So any one option you can take. So never make this mistake that you are mentioning both the exact value and the value of the derivative of that variable it at a point, be it temperature, be it velocity, anything. You cannot you cannot mention the flux and the value of the variable itself at the same point. So if at a wall your heat flux is fixed, then you have to find the temperature of that wall from the mathematical formulation, and if the temperature is fixed, then you have to find the flux at the wall from the mathematical formulation. So just let us go back to the problem to judge that which boundary condition should be there at x equal to delta t. What should be the boundary condition? Okay, so we have to go back, and here is the question. So in the question nothing is said explicitly about what is the boundary condition at x equal to delta t, but we can see that here it is given that at this position, okay, at this position it is given that it is T infinity. So I think in the question paper also it should be explicitly given. Okay. Now ideally, mathematically, the boundary condition should be T x tends to infinity is equal to T infinity, or delta T delta x at x tends to infinity is equal to 0. Okay, but here to solve it, these conditions are okay. So here we will consider this one, okay, from the question. Now can you tell me, okay, so I will not say this before telling all the obvious boundary conditions. Okay, that is, we will derive the derived boundary condition. If you have seen the previous video, then you will be knowing that what do we mean by a derived boundary condition, but I will do it at the last. Okay, so for x we need two boundary conditions and we have got. So now can we get the initial condition? So the initial condition should be T for all x, so that will be 0 to infinity and T T equal to 0, that is why it is called an initial condition, is equal to T infinity. Okay, now if you do up till this, your first part is over, but the non-dimensionalization is remaining. So you have to define uh, some variable with respect to which you will define your non-dimensionalized variables. So that is your homework. I mean seriously, I have done it for many times. Okay, so that is your homework, is the non-dimensionalization of governing equation, okay, and boundary conditions, okay, and initial condition obviously. Okay, so now let us see the derived boundary condition. Okay, so the derived boundary condition. So can you tell me that, can we write here this one? Because in the previous problem we had this this one at x equal to 0 for any time t greater than 0 equal to 0. So this was the boundary condition which we were having in the previous problem, but can we have in this problem? So if you are someone who is giving the argument that delta t delta x is given as minus q by k, which is a constant, then I can write this one at x equal to 0. Can we write this? No, we cannot write this, because consider a function f that is equal to delta t delta x. Now if I say you that you find del f del x at x equal to 0, if I ask you to find this, so what will you do? Will you first find this and then you will put x equal to 0, or will you first say that what is f of 0, then you will be find del f0 of del x. So what you will be doing? You will not be doing this thing, right? You will be doing this thing. That is why even if my del t del x at x equal to 0 is a constant, I cannot say surely that this is 0, that this is 0. Okay, I cannot say this surely. Clear? So that means this is not a derived boundary condition. So let us explore another boundary condition. I mean, let us explore the second derivative of the temperature at x equal to delta. So now we have to find this at x equal to delta. and t greater than 0. So what will be this? Now we know that t at x equal to delta is equal to t infinity as per our boundary condition. Okay, for any time t greater than 0. Okay, so I should be write that also. We know this, and this is a constant. That means I can write this is equal to 0. Okay, now if you put this in your governing equation, that means now I can say surely that this at x equal to delta for any time t greater than 0 is equal to 0. So this is my derived boundary condition. So this was also a very important part, derived PC. Clear? Okay. So now we have how many boundary conditions? 1, 2 and 3. Okay, actually we can have this boundary condition also, because I mean this boundary condition is essentially greater than equals to delta t. Okay, so then we can have actually this one. Okay, so we can have 4 boundary conditions actually, but let us work with the 3 boundary conditions only, because I will say you one more thing. So this was our solution for the first part. Your homework is to non-dimensionalize it. Okay, now let us go to the solution of the part B. Okay, so in part B, what do we have? We have to show that the temperature profile can be shown as this one, that is t, that is a function of x comma t minus t infinity is equal to C1, which is a constant and that is a function of time, into 1 minus x by delta t whole square, right? We have to show this. So now can you see that here the temperature profile is a function of x, and the highest order of x is here x square. So we have to now propose our temperature profile, and now I will define a non-dimensionalized variable here, and now you know that why I am doing that, just to reduce my algebra. This will be this by Tref. I don't know that what is this Tref. Okay, and now I can propose this is equal to a x bar square, where this x bar is x by delta. So I have already proposed you the non-dimensionalized variable for theta and x bar, but you have to do it for the tau also, because in the question in the part A they have asked that you have to write the non-dimensionalized governing equation and boundary conditions. So you have to non-dimensionalize all the variables, not only x, I mean, and temperature. You have to non-dimensionalize the time also. So here we will define it like this. And why a second order curve? Because you see that here also we have a second order curve. Okay. Now for x we have 3 boundary conditions, 2 exact boundary condition and one derived boundary condition, and in this equation we have 3 variables. Okay, so 3 unknowns. So let us see that can we have one more boundary condition, then we can go for 1 degree higher accuracy. Okay, so at x equal to 0 we cannot have any more boundary condition. We can have one initial condition, but we cannot have any boundary condition. At x equal to delta t we have this one and one derived condition. Now you can actually tell this one also. Okay, but we don't need, I mean technically this is not correct to mention both the flux and temperature in at a particular point. Okay, but from the point of view of intuition you can see that. Okay, so let us try to apply the boundary conditions here. See, if the second order curve is not giving the result that we want, then we can try for a third order curve also, that is a cubic approximation. So that means from here our del theta, or I can write here d theta dx, because theta is only a function of x bar, so it will be 2a x bar plus b. Okay, and if I write this one, this will be only 2a. Okay, so now let us write the boundary conditions in terms of theta and n x bar. So the first boundary condition is theta at x bar equal to, okay, so del theta, okay, del x bar, or I can write obviously d theta. Actually theta is a function of, okay, that is fine, lx x bar equal to 0 is equal to what? Now if you have already written here theta, then you have to multiply one t ref and here one delta. Okay, and a minus k was already there, so I will write it here as minus q naught by k. So then you can see that when I can write this as minus 1, when I can write that, okay, I can write if I define my t ref is equal to what? My t ref is equal to q naught delta by k. If I write this, then I can write this one. So to make this governing equation like this non-dimensional governing equation like this, I have defined the T ref like this. So from now my non-dimensionalized temperature is defined by T minus T infinity by Q naught delta by K. So have you understood that how I found the T ref? Okay. Then we have another boundary condition, that is saying this at x bar equal to 1 is equal to 0, because t at x bar x equal to delta was t infinity. So if you put that thing in this boundary condition, then you will get 0. And the derived boundary condition was this thing. Okay, so this at x equal to 1 is equal to 0. So let us now copy these three equations and put them beside our boundary conditions, and let us apply them. Okay, so I will make it a small. Okay, so first let us apply this one, that is d theta dx bar. Okay, at 0 is equal to minus 1. So this will give 2a into 0 plus b is equal to minus 1. Then I am getting my b equal to minus 1. Okay, now let us apply the second one, that is theta at x bar equal to 1 is equal to 0. So I will get it from this one. So that means a plus b plus c is equal to 0. That means my a plus c is equal to 1. Okay, now I will write the third boundary condition and apply that. So this at x equal to 1 is 0. Okay, so here okay, so this is a constant. I am seeing that I am getting this as a constant. So this is suggesting that my 2a is equal to 0. That means my a is equal to 0. But I know that my a cannot be equal to 0, because it has to be a quadratic curve. Okay, so if I don't want that, then what I will do now, I mean, I can see that my second degree approximation will not work. Okay, then I have to take something theta star, that will be m x bar whole cube plus n x bar square plus p, okay, plus p. Let me see if I have done all the algebraic things correctly or not. 2x, yes, I have done it correctly. Okay, So plus p x bar plus q. Okay. Now let us apply all the boundary conditions. Now we need 4 boundary conditions. Okay. So we will apply this also here. Oh, and which boundary condition? That is this one. This one. We will apply this one also. Okay. No, actually, can we apply this one at x equal to 0? Okay, we have to apply this one because we don't have any other choice. Okay, so we have another set of boundary condition here, and that boundary condition is, let me write it here. Okay, that is del theta, sorry, d theta dx bar at x bar equal to 1 is equal to 0. Okay, so let me write it. I mean, what I will do is I will again consider this ones and copy, and I will paste it here. Okay, so let me make it even smaller, but I hope that you can see it comfortably. And I will have another boundary condition. Sorry, I have copied the wrong things. Okay, so first let me find out the derivatives so that we will not make any mistake. So this will be 3m x bar square plus 2n x bar plus p. Then we will have d2 theta star dx bar whole square is equal to 6m x bar plus 2n. Clear? So now let us write the boundary conditions, or let me just copy it. Okay. So if I just copy the boundary conditions, this one, the boundary conditions, where, okay, let me just write the boundary conditions once more with this color. So d theta star dx bar at x bar equal to 0 is -1, theta star at x bar equal to 1 is 0, and d theta star dx bar at x bar equal to 1 is 0, and d2 theta star. Okay, so up till now, if you have found any boundary condition other than the third one that I have written, then please let me know, because writing these two things are not very scientific. Okay, so if you have found any other boundary conditions, so let me see once that if I can find any boundary condition. So at x equal to 0 I cannot mention temperature because I don't know that. At x equal to delta t, these two options are there, and we can have a derived boundary condition. Can we have any derived boundary condition at x equal to 0? Can we have? Actually, no, we cannot have. Okay. Here, this equation we got not because t is not a function of x. We got this one because of this thing. You remember? Okay, because t is not a function of time at x equal to delta, that is at the heat penetration depth. That is why I got this equation, and not because of x is, I mean, not because t infinity is not a function of x bar or x. Okay, I mean, these mistakes we can make, actually I can also make. That is, we can think that t is not a function of x, and that is why we are getting this, but not, that is not the thing. This is not a, I mean, this is 0 at x equal to delta. That is why we can say it that this is also 0. Okay, so I think we cannot have any other boundary condition. So let us apply these ones and let's see that can we arrive at the desired result or not. So still I am just urging you that go through the problem again and see that if any other uh, boundary condition you can see that I am maybe missing. Okay, because I have not revised it as I have uh, told you before. Okay, so now let us first apply this boundary condition, is this one, and if we apply this one we will get what? P is equal to -1. So you see this one and this equation, right? Now if you apply this one, then you will get, okay, if you apply this one, then you will get m plus n plus p plus q equal to 0. So m plus n plus q is equal to +1, okay, from this equation. Now if you apply this equation, okay, then you will get what? 3m plus 2n plus p equal to 0. So 3m plus n plus p equal to 0. 3m plus 2n, okay, from this equation, from this and this third equation, 3m plus 2n, okay. So 3m plus 2n is equal to 1, okay. Now let us apply the fourth one. So you see at this equation and in this equation. So my phone battery is dying, but we will not have a problem because my charger is there today, so don't worry. Let me take this color now. So here now we will get 6m plus 2n equal to 0, right? So 6m plus 2n is equal to 0. I think I have done it correctly, right? So this can boil down to 3m plus n equal to 0. So from these two equations it was 0, right? And okay, this is fine. So from these two equations, which this one and this one, I can write that 1 minus 2n is equal to minus n, right? That means my n is equal to 1, okay. So I got this also, I got this also, and I have also got p is equal to -1, okay. So I got this also, and now if you put this value of n and p in this equation, then you can get the value of m also. So from this equation you can get the value of m. So m is equal to minus p minus 2n by 3, right? So that will be equal to minus p means 1, so minus 2n means minus 2 by 3, so that will be equal to minus 1 by 3. So m is equal to minus 1 by 3. Clear? And we use this equation now, this one, to get the value of q. So q is equal to 1 minus m minus n. So q is equal to 1 minus m minus n, that is 1 minus, so 1 plus 1 by 3 minus 1, that means 1 by 3, okay. So that means q is equal to 1 by 3, right? So that also we got. So now if we put these values in our assumed temperature profile, okay, So mn pq, right. So then if we write this, then theta will be m is minus 1 by 3 x bar whole cube plus what, mn, so x bar square, p is minus 1, so minus x bar plus 1 by 3. Clear? So it is more like 1 minus x whole cube, right. So I think there is a mistake, so let me see the question once more. Was it something else? Just let me see. Okay. No, it is given as square, that is fine. So it can be the case that we are making some mistake, but I think you are getting the I mean process, right? Because if we are making some mistake, I will check it once after the lecture, and if I find some mistake, then I will convey that to you in the next lecture. Okay. So up till now we are getting this only, and now see, if I multiply by 3, multiply by maybe minus 3, we will have x cube minus 3x square plus 3x plus 1, sorry, minus 1, right. And this is the formula of x minus 1 whole cube, right. And what is your theta? That means theta means this is your minus 1 by 3, or if I take the minus inside of this cube, it will be 1 minus x whole cube, right. Now this theta, the definition of theta was t minus t infinity by q naught delta by k, right. So that means this is this 1 by x whole to the power cube, right. Now if I can write this thing, then okay, so t minus t infinity is what, 1, okay, so q naught delta by k, 3k into 1 minus x bar whole cube. So in the expression we were to prove t minus t infinity is equal to c1, that is a function of time, into 1 minus x bar whole square, where this x bar is x by delta. See here, this delta is a function of t, that means I can say this one as c1, okay. The only difference is I have got a cube here and not a 2 here, so I can I mean there can be an algebraic mistake also. Let me just once more go through the algebra. So have I written the boundary conditions correctly? Yes, I have written the boundary conditions correctly. Now this, from this equation, this will be minus 1p, and now from this equation I will have m plus n plus p plus q equal to 0. Then that means m plus n plus q equal to minus p, and minus p equal to 1, that is fine. And for this one, this one is, from this one I can write 3m plus 2n plus p is equal to 0. So 3m plus 2n is equal to 1, that is also correct. I think that is correct, right. Okay. Finally for this one we have to use this equation, and from this also I have done it correctly. So this is 6m plus 2n is equal to 0. 6m plus 2n is equal to 0. I think all the things are fine, okay, but still if you, so 3m plus 2n is equal to 0, is 2 into, that means 3m plus n is equal to 0 if I take 2 common. So now I know that p is equal to minus 1, so but from these two equations I can write that my 1 minus 2n is equal to minus n, right? So that means I can write n is equal to 1, right? Okay, and if my n is equal to 1 and I know my p, then from this equation m is equal to minus p minus 2n by 3. So this will be 1, n is 1, so this is minus 1 by 3, correct. And finally, so I will see it once more, okay, that where we are doing the mistake. So can I write that this is 0? No, this we cannot write. Let me see why we are not achieving this. One thing that can be the question is wrong, okay, but theta star is this. Uh, so theta star is a constant. Okay, let us see. So up till now you just consider this, but this will be the method only, okay, you just consider this. I will see in the next lecture if I can do something or not, but up till now you consider this as your result, okay. So now let us proceed for the part C. In the part C you have to develop the integral equation, and I told you, or I will tell again, that you have to develop the integral equation from the dimensional part first. That will help you actually. You can do it from the non-dimensional part, but it will unnecessarily complicate your calculation. You can try that. I failed by doing that in the last uh, lecture, but I think that can be done. You can try it by yourself, okay. So now the step is we have to integrate this. So why we have to integrate this? The philosophy behind that I told that in the previous video. So 0 to delta. Now perform these parts very carefully. Alpha into this at delta minus this at 0. Okay. Now that is equal to, okay, now I can write this as directly, or I have to write here battery has gone down to 10%, but we don't have any worry about that. So this is d small t, sorry, this will be this thing. So now this actually we don't know, okay, so we can keep it like this at delta, or okay, so I have done another mistake, sorry. So from Leibniz rule we can write this actually as, so I have taught the Leibniz rule before. So this is actually this is equal to this, okay, this is now, okay, d delta dt, t at x equal to delta and any time, okay, plus d0 dt, and this is t of 0 and t. So we don't need to write that, or I can directly cut this as 0, okay. And we actually know this one, this is t infinity, clear, okay. So now you see that we can have alpha. So now let us write this as this one, but this we know, this is equal to minus q naught by k, right, and that is equal to what, d dt of 0 to delta t dx, okay, minus of, okay, now I can write this as d dt of 0 to delta dx, and there is a t infinity. I can also, okay, so firstly I will write this t infinity outside this, but I can take this infinity and rather, in fact, I will take this inside because t infinity is a constant, it is not a function of x. Okay, and now I will put this as 0. Okay, otherwise I will not be able to solve this. Either I have to know the value or I have to put this as 0. Okay, so I will have q naught alpha by k is equal to what? Is equal to d dt. Okay, so in the previous one, in the previous problem, I was knowing that this was equal to 0, but this value I did not know, that is the flux, right? Okay, so for your understanding only, I will just go in the last thing. Okay, see, here we were having this one. For this problem, this is 0. Sorry. For this problem, this is q naught by k. But now this is here. I cannot put it 0. Okay, I cannot put it 0. Right? But here I did found it as minus 3 by 2. How did I found it? How did I find it? That is, my theta was some approximated function, theta is equal to a x bar q plus b, and now that the moment I know this a b c d, then I can found my del theta del x bar, then I can find this. Okay, but here we don't have to do those things because we have already approximated that my this thing is 0, this thing, sorry, that my this thing is 0 and the value of this we know. Okay, so that is fine, and this value will come as, now I can write this as t minus t infinity into dx, 0 to delta. Clear? So what I can do is, now see very carefully that what I am doing. This will be d dt. Okay, now I will transform the integral, the variable with respect to which it is being integrated, to x bar. So I will write d of x by delta. I will multiply a delta here. I can take this out of the integral because delta is not a function of x, and also I can I can divide a q naught by delta k. Then again I have to multiply one extra q naught by delta k outside. Okay, so first let me close the bracket. I will multiply the extra q naught by delta k here. Okay, fine. Then it will be what? Q naught alpha by k is equal to q naught delta square by k d dt of what? 0 to 1 theta, or theta star rather, the second one, dx bar. Okay, so these things will get cancelled out, right? Q naught k k, right? Okay, so then this will be some again we should have a t, oh no, is that fine? D, okay, another mistake I have done, a terrible mistake, that is, I'm very sorry. Maybe I'm not into my mind today. I am really sorry for these things. Okay, q naught by k, because see, this delta is not a function of x, because of which we can take this out of this integral, but these deltas are function of time, so we cannot take this delta square out of this. Okay, so this delta square should be here. Okay, or let me write it very much clearly. So d dt of, okay, delta square into this whole thing. Clear? So then this will be cancelled out. I will only have my alpha equal to, okay, d dt of, okay, delta square into some constant. So this will be some constant, because now we know that my theta star is what in terms of x bar, we know, and we know m and pq. So now we know this expression. Okay, so this is my actually theta star, not theta. This is theta star. Okay, so now as we know this as our theta star, so that is 1 minus x bar whole cube by, okay, so that, I mean, I can write this here, that is, this is 1 minus x bar whole cube by 3. Okay, so this thing, this whole thing, okay, this whole thing will be a constant. I will denote by capital A. Okay, this will be capital A. Clear? And that is nothing but your, so now you can write d of delta square into A, that is equal to alpha del dt. That means if I integrate, that is my delta square A is equal to alpha t plus some constant, maybe c dash. Now at t is equal to 0, there would be no heat penetration depth. That means my c dash is 0. Okay, so my delta is equal to alpha by a t whole to the power half. So let me find the a also for the sake of completeness of the problem. A is equal to 0 to 1. Okay, 1 minus 1 minus x bar whole cube. I can take this 1 by 3 out of the integral. Okay, so this will be what? Sorry, there was one dx. So 1 minus this whole to the power 4 by minus 4. So this will be minus 12. Minus, okay, so, and also the limit will be 0 to 1, right? So I can write it as, take the minus 12 common. If I put 1 here, then I will get 0. If I put 0 here, then I will get 1. So then I will have here 1 by 12. A is 1 by 12. That means if I put this A in this equation, then I will get my alpha as 12 alpha t whole cube. So this is my final answer for this problem. Okay, so this is enough. I mean, this is enough for today, and I will see, and you must also look for another boundary conditions if you can get other than these two. Okay, because I personally feel, I can see, I never say that I know everything. Okay, I have also studying, I mean, I have also studied the thing, and I am also studying right now, and I am also learning the things. So I am just trying to convey the things to you. You can be someone who knows better than me, and you can find out my mistakes in this lecture video. And I have no shame, I have no false pride that I cannot make any conceptual mistake. I know everything. Believe me, I personally believe one sentence, that none of us, honestly none of us, considering the great scientists also, know the exact behavior of the nature. We can mathematically say that we can mathematically model this thing up to a particular accuracy. So no formula in the world is there which is 100% correct. Okay, so we at most can try to model nature, but we cannot go above our mother nature. So I can also have conceptual mistakes. So please, if you know the things that he is saying this thing wrong, please tell in the comment box. Okay, that will help others also. And one more thing, the moment you say something that this is not correct, either you give the justification, or if that is a factual thing, please give the source from which others can refer to that. Okay, so that is very important, otherwise that can create confusion. Okay, so I am having confusion that I cannot take these two simultaneously, but still, if you are someone that you know that, I mean, if you can find any other boundary condition, or if you can give me the exact logic that can I take this one or and this one simultaneously. I mean, intuitively this seems correct, but mathematically we cannot define both slope and the exact value of the variable at a particular point. That is what I think, but still, as physically it seems correct, and also we are not getting the exact result. So it should be square here, but we are getting the cube. But it can be the case that the question is also wrong. So you should be uh, taking care about the approach and not about the answer. If your approach is correct and you have done this thing totally in your examination, you will get at least 15 out of 20, at least. Okay, so I can share you some story. When I was studying, so this question paper was when I was in my M.Tech first year. So when I was uh, giving my exam, advanced conduction exam, and I was solving this question, I thought that I have to somehow show that this profile, that is my C1 into uh, where is that profile, that is this one, that is my C1 into 1 minus x bar whole square, I have to somehow show that this is a valid profile. Now I know that if it is a valid profile, if it is satisfying all the required boundary condition. Okay, then I showed that this is satisfying the three boundary conditions, that is the two exact and the one derived. Okay, now when I was seeing my copy, I got 15 out of 20. I then asked sir, why I have done all the parts. Then sir told me that you have to apply four boundary conditions here and taking a cubic equation, and you have to derive that. So then I understood that I have to satisfy the most amount of boundary condition. If I want to say that this is valid, then I have to satisfy the maximum number of boundary conditions. So this criteria I have told you in the earlier video also. Okay, so then I understood that I was to derive this one, not just showing that. I mean, if you just put here x bar equal to 1, okay, then it is coming as 0, and we also know that theta at x bar equal to 1 is 0, you see. And likewise you will see that it will satisfy all other boundary conditions also. Okay, so with that I would love to end this lecture. Okay, so before ending, I will just give you a hint about what we are going to do next in the upcoming lecture. That is, we will be seeing the exact solution. But how can we get the exact solution? Now the hint is, can you tell me some transformation, maybe like x tilde is equal to some c1 into x plus c2 or anything, and my t tilde is equal to c2 into t, my capital T tilde is equal to c3 into t. So can you, or it can be e to the power ct, anything, any type of transformation. Can you give me a set of transformation? Can you give me a set of transformation because of which the solution for x, okay, sorry, the solution for t x comma t is equal to t bar x bar t bar. Okay, 3% battery is remaining. I have to connect the charger. Although I will be just ending this video, but still I have to connect the charger. Okay, so again my question is, can you come up with a transformation which will give my t as a function of x and t is equal to my transformed variable solution? So my original solution should be equal to the transformed variable solution. Can you give me some transformation like that? This is the motivation for the exact solution. Okay, so I will continue with this in the next lecture, and most probably if I don't find any severe mistake in this approach of this problem, then the next lecture will be our last lecture. Okay, and that will be a bit long lecture. Okay, at least 1.5 hours. So up till that, take care, goodbye, and thank you.